In this video, let's explore partitioning, the various partitioning techniques are used in distributed systems, and the benefits of partitioning. Partitioning in distributed systems involves dividing large data sets or workload into smaller partitions for better performance, availability, and scalability. What we call a partition here is called a shard in MongoDB and Elasticsearch. It is also known as a region in HBase, a tablet in Bigtable, a vnode in Cassandra and React, and a vbucket in Couchbase. So, not to get confused, they all mean the same. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Let's dig deeper to understand the benefits of partitioning. Partitioning a data set distributes it across multiple nodes or machines in a distributed system. Each node handles a specific partition, enabling parallel processing. This boosts performance and reduces processing time. Partitioning helps evenly distribute the workload across the nodes in a distributed system. This load balancing approach ensures that no single node is overloaded while others are underutilized. This maximizes system performance and resource utilization. Partitioning lets a system scale horizontally. This enables the system to handle more data or users. To know more, watch our video on scalability. Partitioning provides a fault tolerance and high availability. Even if a portion of the system becomes unavailable, the remaining partitions and nodes can contribute to function, maintaining the overall system's availability. Partitioning can also be used to optimize the data locality, where data is stored and processed closer to the computing resources. Data locality minimizes the data transfer across the network, reducing latency and improving the overall system performance. Partitioning techniques vary based on the specific requirements and the characteristics of data and the distributed system being used. Let's discuss some of the common data partitioning techniques. There are two different types of data partitioning: vertical data partitioning and horizontal data partitioning. Vertical data partitioning, also known as column partitioning or column based partitioning, is a data partitioning technique where a table is divided vertically based on columns. In this approach, columns with similar characteristics or access patterns are grouped together in separate partitions. Normalization is one way to perform vertical partitioning. Let's consider an example of vertical partitioning in the context of an e-commerce application that manages customers' information. In a traditional table structure, you might have a single table called customers with columns such as customer ID, name, email, address, phone, and order history. All these columns are stored together for each row representing a customer. With vertical data partitioning, we can partition the table based on the logical relationships between columns. Let's say we decide to vertically partition the customers table into two partitions: personal info and order info. Vertical data partitioning is typically performed on user profile, product catalog, and customer related data in e commerce, and patients' records and medical data in healthcare. In horizontal data partitioning, a table is split into smaller multiple tables, where each table contains a subset of the original table rows. These subsets are then placed on different nodes. Some of the popular horizontal data partitioning techniques are range partitioning, directory based partitioning, hash partitioning, and partitioning based on consistent hashing. We will be discussing each one of these in detail. So don't go anywhere and stay tuned. In range partitioning, data is divided into partitions based on a specific range criteria. Each partition then contains a predefined range of values. Let's consider an example of range partitioning in the context of a sales database. We have a table named sales data with columns order ID, order date, customer ID, product ID, and quantity. To apply range partitioning, we divide the sales data table based on the order date column, which shows when each order was placed. Here is how we split the data into three partitions. First partition, recent orders, containing the last 30 days orders. Second partition, historical orders, which contains orders from 31 to 365 days ago. And the third partition, archived orders, containing orders older than 365 days. Each order is stored in the partition that matches its order date. New orders go into the recent orders partition, and as time passes, orders move to different partitions based on how old they are. Google's Big Table and Apache HBase seem to leverage range partitioning. However, range partitioning has its limitations. In range partitioning, efficient range queries can only be done using the partition key, not other keys. Plus, if a big range spans multiple nodes, query performance suffers. Also, data distribution may be uneven if one range has more data than others. In a directory-based sharding, the data items are distributed across the shards based on explicit mappings maintained by a centralized directory or metadata service. This approach is beneficial when there is a need for a centralized control over data distribution and routing in a distributed system. Consider an example of directory-based sharding in an e-commerce sales database. We have a distributed database storing sales orders across multiple shards. Instead of a predefined ranges, a central directory maps each order to a shard based on its ID. When accessing or modifying data, the directory routes a request to the correct shard. Directory-based sharding centralizes control over data distribution, but the directory becomes a single point of failure. Google's Spanner and Amazon's DynamoDB uses directory-based sharding. Hash partitioning divides the data into partitions using a hash function on a column. For example, Cassandra and MongoDB use MD5 as the hash function. Let's consider an example of a hash partitioning a customer database. We have a table called customers with the following columns: customer ID, name, email, and city. To apply hash partitioning, we partition the customers table based on the customer ID column. The partitioning process involves the following steps. First step, determine the number of partitions. Let's say we want 4 partitions. Then second step, define the hash function. Choose a hash function for the customer ID column. Lastly, apply the hash function to each customer ID. This way, each customer record gets assigned to a partition based on its hashed customer ID. Choosing the right partitioning key and hash function is vital in hash partitioning to ensure the data is distributed evenly. Constant hashing is a smart way to distribute data across many nodes without the need to move the data around when nodes are added or removed in the cluster. It works by using a hash function and a circular structure to assign data to partitions. Let's illustrate consistent hashing with an example of a distributed cache system. Suppose we have a distributed cache with 4 nodes A, B, C, and D. Each node represents a partition. The partitioning process involves assigning nodes, where we create a circular ring representing all possible hash values. Each node is placed multiple times on this ring based on its hash value. After that, mapping data. When storing or retrieving data, we hash its key to get a value. This value is then mapped onto the ring to find the corresponding node. Now, let's understand how the partitioning using a consistent hashing works when the cluster changes. That is, when we add or remove nodes from the cluster. If we add a new node like E, its positions on the ring are determined. We adjust the positions between existing nodes to balance the load, minimizing the data movement. If a node fails, like C, its keys are redistributed among other nodes. Only a fraction of keys need to be moved as other nodes take over some of the failed nodes' responsibilities. Consistent hashing is widely used in distributed systems like caches, databases, and CDNs. We have explored data partitioning, but how does a client find the right node to connect to for a request? Also, the allocation of partitions to nodes varies after rebalancing, which the client is unaware of. So, how does a client find the right node to connect to? This is called service discovery. There are a few methods to handle this. Let's discuss them. In one approach, clients can request any node. If it does not have the data, it forwards the request to the correct node. Another approach is using a routing tier. Requests are sent there first, which then directs them to the appropriate node. And the last approach is that the clients already know which partition is on which node and can connect directly. But keeping track of node changes is a challenge. Solutions like ZooKeeper help manage these updates. We have a separate video explaining how ZooKeeper manages Apache Kafka cluster. Please watch that to learn more. Sharding or partitioning helps systems scale and improve performance, but it adds complexity that may not always be necessary. Here are few alternate approaches. First approach, vertical scaling, where you upgrade single database server with more resources like CPUs, memory, and storage. This is easier to manage than sharding, yet allows a significant expansion. Second, SQL optimization, where SQL queries and database schema are fine-tuned for better performance. Third, caching. Employ in-memory caches such as Redis to lessen database load by avoiding frequent queries. And fourth approach, use combination of read replicas and load balancer. This offers a horizontal read scalability without full sharding complexity. Also, it distributes reads across replicas. In conclusion, partitioning optimizes distributed systems' performance and scalability. Understanding options like range partitioning, directory-based partitioning, hash partitioning, and consistent hashing enables architects to design robust distributed systems. If you found this video helpful, give us a thumbs up and subscribe to our channel for more such interesting topics. Do check out our other videos on software performance optimization case studies, coding, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time.